Hi everyone, I'm Akash Saravanan and I'm here to talk about Pixel VQ-VAEs for improved pixel art representation. I worked on this alongside Matthew Gusdale at the Grail Lab at the University of Alberta in association with AV. So I'm just going to run you through okay, this is, I hope this is visible, but either way, I'm going to just introduce what the general domain is, talk about some related work, talk about the Pixel VQ-VAE, which is our main contribution, and talk about some evaluation things. So first off, what is pixel art? I'm assuming most of you are familiar with pixel art, but in either way, pixel art is just a particular art style where you have a restricted color palette and these visible pixels, as you can see here. You can see each individual pixel. And this is kind of important because like if you look at this line of pixels over here, without that line of pixels, you can't really see a mouth. So each pixel here is kind of important. And the other side of the topic is representation. Representations are also called embeddings, and they are essentially just a way of, representing something as numbers. So for instance, we could take this giant image, pass it through a model and get a bunch of numbers. We could then use these numbers for a bunch of tasks, such as this remaking this image or creating new images and stuff like that. Now, a natural question is why we might want to represent something. Why not just generate new Pokemon or generate new images? One thing is with a single representation, we can have multiple applications such as generating new things or transforming things or generating text, stuff like that. And as to why we work on pixel art in particular, there are some issues. First off, there just isn't a lot of work on pixel art or representing pixel art. Second, the primary method that's used, VAEs, aren't great. They tend to be kind of blurry. Third, there are some other models, but they are not great for pixel art. And a reason for this is that CNNs, which a lot of these works use, process neighboring clumps of pixels together. And the issue with this is we don't want that. We want each pixel to have focus because like I mentioned, every pixel kind of does matter. So the main contributions of our work here are first the usage of VQ-VAEs for pixel art. I'm going to talk about VQ-VAEs in a bit. We also introduced the Pixel VQ-VAE, which adds two enhancements to the VQ-VAE. We evaluate this on multiple baselines, and we also show its usage in downstream tasks. Quick preview here. We primarily work on the Pokemon dataset, and I go into that in a little time. But let's just talk about some pixel art stuff. There isn't a lot, but let's look at them. So this first work is not actually pixel art, but it's on representing images and transformations. So this work by Gonzalez et al. Attempted to modify Pokemon, and you can see it works somewhat well, but it's kind of blurry and they use a VAE. There's also this other work by Horsley and Perez Libana on generating images, pixel art images using a GAN. And while these have some structure, they don't have a lot of detail. There's also other works such as image transformation by Pokemon to Pokemon by Riley Wong. And here they swap the color palettes between Pokemon. But while this works well, it's kind of restricted in that it's the only thing you can do with it. And as for the VQ-VAE itself, I want to sort of take your attention back to a normal autoencoder first. So an autoencoder takes an image, passes it through the encoder, and you get a representation. You can then use this representation to reconstruct the image. VQ-VAE is kind of similar, except it learns a discrete representation. So instead of having 0.5 and 1, you instead have normal numbers like 3 or 2 and stuff. Now, this has some interesting results. I'm not going to go too much into the VQ-VAE itself because it's a bit complex. But one interesting thing about the VQ-VAE is that it kind of represents each part of an image as an encoding. So for instance, the top left thing might correspond to some number. The numbers here are just random numbers that I typed. They do not match to this. But each of these blocks correspond to one particular number here. So this at extreme level, this allows us to represent each pixel in the image by a single number. This gives us a lot more fine-grained control over the entire image. Now, the Pixel VQ-VAE uses the standard VQ-VAE architecture, but we introduced two extra enhancements that improve performance on pixel art. The first is the pixel site block. So this is specifically to target pixel art performance, and we use a 1x1 convolution to do this. Now, historically, these convolutional layers have been used for downsizing and dimensionality reduction. Whereas in our case, this is actually helpful for us because 1x1 convolutions look at each individual pixel, and that's exactly what we want. Now, the adapter layer is mainly due to a quirk of the VQ-VAE, which I go into a bit more detail in the paper because it's a bit complicated to explain. In terms of data, we use the Pokemon dataset, which is essentially a compilation of sprites from multiple Pokemon video games, such as the ones you see here. We do a fairly standard pre-processing loop where we split the data into train, validation, and test. We resize them to the same size. And we use 4 different backgrounds for data augmentation, a black background, a white background, and 2 noisy backgrounds for training. We also perform some random rotations for more data augmentation. In terms of models, we train 3 different models. The first is the Pixel VQ-VAE low resolution. So here, each of those encodings that I mentioned earlier correspond to 16 pixels in the image. This results in a lower resolution model. This model uses 2 convolutional blocks alongside R2 enhancements. The medium resolution is similar. It uses 1 convolutional block and each encoding corresponds to 4 pixels. And in the case of the high resolution, each encoding is 1 pixel, like I mentioned earlier. Now, an interesting thing about the high resolution model is that it doesn't use any normal downsizing convolutional blocks. It just uses a single 1x1 convolution blocks that kind of works a bit like the pixel size layer and the adapter layer. Now, in terms of evaluation, let's first look at the representational quality and let's look at some images. So I hope these images are visible, but these are all on the test set. This first column here is the original image. The second column is our first baseline, which is a normal VAE. The remaining columns are the VQ-VAE and the Pixel VQ-VAE. The VQ-VAE is our model without the enhancements that we introduced. And as you can see here in the final column, the Pixel VQ-VAE high-res is pretty similar to the original image. There's very few differences. Whereas if you compare the Pixel VQ-VAE medium res versus the VQ-VAE medium res, you can see that there's something of a background in this image. Now, again, we don't have a high-res version of the VQ-VAE because there are no other layers apart from our enhancements. Let's also look at some numbers because images aren't everything. So we use 2 metrics here, the mean square error and the structural similarity index. The mean square error is a per pixel loss function that helps us to get a bit more information about how close 2 images are, whereas the structural similarity index gives us an idea of the structure of the image. Now, if you look at this green color table here, the green color column here, which shows the mean square error, our high-res model significantly outperforms everything, including the baselines. Whereas in terms of structure, our medium-res model actually does a bit better than the high-res model. This is mainly because the high-res model focuses on individual pixels, so it has a side effect of not focusing as much on overall structure. Now, we also use these, we also do an ablation study. So here we essentially test out our model with no enhancements, with 1 of the 2 enhancements and both enhancements. And as you can see in the case of the high-res and the medium-res models, our model does do the best. In the case of the lower resolution models, it's interesting because the numbers are pretty close to each other. This is more of a factor of the fact that these are very low res in nature. As you can see from like the previous image, there's not a lot of detail there, even though it does acquire roughly the same shape. We also use these learned representations on 2 different downstream tasks. The first is generation. So we use 2 baselines, the VAE from before, which we are not going to talk about, the DC GAN, which is similar in architecture to unpublished works that work on generating new Pokemon. You can see on the DC GAN here that it generates vaguely Pokemon-ish shapes, but there's no pixel art aspect of them. They're just weird blobs. Now, the rest of these images are also weird blobs, but they do have pixel art in them, which is great. Now, the Pixel VQ-VAE high-res in general does have like more detailed blobs. Like for instance, this could be seen as some sort of humanoid creature, I guess. But in either case, it shows us the pixel art aspect of the dataset. In terms of numbers, we use the FID score to measure this. FID is a metric used for generative models that compares generated images against the training distribution. Now, the FID was created for photorealistic images. It's not the best metric for pixel art, but there's no better metric that we know of. If you see over here, the high-res model does have the best value, and the GAN is a little worse than it. But another thing to note is the parameters. Our high-res model is actually just 50,000 parameters. But we do use a pixel CNN for generating images for the downstream tasks. So that has about 13.5 million parameters. But even combining these two, it's still lower than the 15.5 that a GAN uses. The other task we check out is image transformation, similar to Pokemon that I showed you before. Essentially, we want to take the colors from one image and put them onto another image. So this third column, the hand of that column, is created by a human. It's from the website PokeColors. Whereas the Pixel VQ-VAE column is the model's attempt at doing this. Now, I will note that I did not train any model for this task. I simply used a mapping function where I took the embeddings for this first image and put them on the image on the second image. So with the model, this would be better, but it still looks reasonably close to the human authored versions. So in conclusion, VQ-VAEs are great for pixel art. Pixel VQ-VAEs are a bit better, and they can be used for a couple of different tasks. There are also some sequels to the VQ-VAE, the VQ-VAE2 and the VQ-GAN. And there are other downstream tasks that we could use this on, such as image classification or text generation. In the context of Pokemon, this could be stuff like setting Pokemon types or generating Pokemon names and descriptions. And yeah, that's about it. Thank you so much for listening to me, and I'm happy to take any questions.